Hello everyone, and a very good day to our lecturer and friends. We are from Group 9 and from the BLM program. Today, we are going to present our video assignment for dynamics and vibration. As you can see on the screen, our group consists of 5 members, myself, Haziq, Farhan, Zahi and Shahid. I will be starting our presentation today. Next, I will start with the question 9. The question asks us to show that all points in a rigid body undergoing translation and have the same velocity and acceleration. To prove this, let's look at the green box. In kinematics, the position of point B relative to point A on the same body is given by the relative motion equation, which is RB equal to RA plus RBA. Next, let's look at the blue box. Because the body is undergoing pure translation, which means no rotation, the relative vector RBA will never change its length or direction. This means it is a constant vector. Because it is a constant, its time derivative is exactly 0. We will use this fact to find the velocity in the next step.
Velocity, taking the first time derivative, gives us the velocity VB equals to VA plus derivative RBA. Since the derivative is 0, this leaves us with VB equals to VA plus 0, which means VB equals to VA. For acceleration, taking the second time derivative gives us the acceleration AB equals to AA plus derivative VBA. Again, adding 0 means AB equals to AA plus 0, so AB equals to AA. This mathematically proves that every point on the translating body shares the exact same velocity and acceleration. Moving on to question 30, we are asked to explain why the work done by a spring force is not simply calculated using the force Fs equal to Ks squared. There are 3 main reasons why cannot just use Ks squared. So the first point is varying magnitude. The spring force changes at every point during its displacement, which is different from having a constant weight pulling an object. Second, constant force assumption. The standard formula W equals to Fs only applies when a force remains constant over the entire distance. Last one, overestimation. If we were to multiply the final force Ks by the final distance S, we would be assuming the spring is at its peak tension from the very beginning. I will now pass it over to my groupmate to walk through the mathematical derivation.
Moving on to the mathematical derivation, to calculate the true work done by variable force, like that of a spring, we can simply multiply force by distance. Instead, we must integrate the force over the path of displacement. As shown in the blue box, the work W is equal to the integral of the spring force Fs with respect to the displacement ds, evaluated from an initial position S1 to the final position S2. Since we know the spring force Fs is equal to Ks, where K is the spring constant and S is the displacement, we substitute that into the integral. Evaluating this integral gives us the fundamental equation for work done by a spring, W equal 1/2 Ks squared, evaluated from S1 to S2. Now let's look into add the comparison table to contrast this with a constant force. For a constant force, where F equals C, the resulting work is simply W equal F times S. However, for a variable spring force, where F equal K times S, the resulting work is W equal 1/2 K times S squared. Now let's look at how we express this conceptually depending on our perspective specifically. The difference between work done on the spring versus work done by the spring. Looking at the left box, we have the expression for the work done by the spring. The equation is U sub 1 to 2 equal negative, open parenthesis, 1/2 K S2 square minus 1/2 K S1 square, close parenthesis. It's crucial to note the negative sign here. The work done by the spring is negative when it's moving away from equilibrium, meaning it's being stretched or compressed. This happened because the first force the force exerted by the spring acts in the opposite direction of the displacement. Conversely, looking at the right box, we consider elastic potential energy. The expression is V equal 1/2 K S squared. This represents the energy stored within the spring itself when it is deformed from its natural unstretched position.
For question 51, a boy slides down a smooth spiral slide. So our known variable are listed on the left, which is mass, which is 40 kg, person radius R, which is 1.5 meter, and the total speed V with a constant 2 meter per second. And the slide drops every 2 meter for every full 2 pi radian turn. So our goal is to determine the force component, the slide digits on the boy at the instant of Fr, F theta, and Fz. So to find these forces, we need to start with the kinematic, which is we need to find the downward slope angle, which is labeled as A. So by dividing the drop by the circumference, we get an tangent A equals to 2 over 2 pi multiplied by 1.5, which gives us an angle of 11.98. So we need to break the 2 meter per second constant into a cylindrical component. So the radius is constant. So the radial velocity Vr, or you can call it R theta, is 0. So and then the transverse velocity V theta is the horizontal component. So it will be 2 cos multiplied by 11.98, which is equal to 1.956 meter per second. So the vertical velocity Vz will point downward, so it will be negative. The way you calculate it is negative 2 sine multiplied by 11.98, and then you will get negative 0.415 meter per second. So finally we need to find the angular velocity theta dot. So we can find it by dividing V theta by the radius R, which gives us 1.304 rad per second.
Hi, my name is Mohammad Shaheen. I will continue on the next part. On this next part, we calculate the acceleration components. Because the slide is smooth, meaning there is no friction, the motion is analyzed using cylindrical coordinates, the radial acceleration, the theta acceleration, and the z acceleration. For the radial acceleration, we use centripetal acceleration relation. A sub r equals negative r omega squared. The negative sign shows that the acceleration acts inward toward the center of the spiral. After substitution, we obtain the radial acceleration of negative 2.55 meter per second square. For theta acceleration, the acceleration is obtained from the rate of change of angular velocity. After substitution, we obtain the theta acceleration of 1.99 meter per second square. For the vertical direction or acceleration, we evaluate the z component of acceleration based on the motion of the boy along the spiral path. By substituting the values, A sub z is equal to negative 0.423 meter per second square. Equation of motion. After finding the acceleration components, we apply Newton's second law, which is sigma f equals ma, along each coordinate direction. First, for the radial direction, I apply Newton's second law along the r-axis. Sigma f in the r direction equals ma sub r. The equation gives the force required to keep the boy moving along the curved spiral path. Here, the force in the radial direction is represented by the normal reaction component of the slide. By substituting the value of mass and radial acceleration, we obtain the value of negative 102 Newton. Next is theta axis. We apply Newton's second law. In the theta direction, sigma f in the theta direction equals ma sub theta. This represents the force balance along the direction of motion around the spiral. By substituting the value of mass and theta acceleration, we obtain the value of 79.9 Newton. Lastly, we apply Newton's second law in the vertical or the z direction. Sigma F in the z direction equals ma sub z. In this direction, we must include the weight of the boy because gravity acts downward. So in the direction of z, the forces include the vertical force component from the slide and the weight, which is mg. After substituting the values, I obtain the value of 375.5 Newton for force component in the z direction. That is all for question 51. Thank you.